the third page. This is okay. This is a presentation.
Okay.
This is the first page.
Yeah, we are able to see only the first page.
So why? So why is it like that? The third page.
Roshanjit, do you know?
Koshi, can you help?
I don't understand.
Hello, Koshi.
Sir,
I can
hello.
take.
Sir, can you please start again, stop sharing and let us start again.
Okay, I'll start again the sharing.
Yeah, please stop sharing now.
New sharing, okay. You see, okay, I'm going to click on.
There is
the green button at the bottom, the stop sharing. Maybe just click the stop sharing once, and then we'll
I have a new, for me, I have a new sharing, and I have a start again the sharing. New sharing.
There should be a button called stop sharing or something.
Stop sharing, okay, but I have not stopped sharing. I have, stop sharing, okay.
Yes, so you stop sharing, start again.
Okay, I stop sharing now.
Yes, yes. Yes.
Okay.
Okay, so now you restart it. I mean, you start again sharing, share screen.
So first you make sure the PDF is open.
The PDF is open. It is on my. It is there.
Okay. So then maybe share screen once more.
See?
Yes. Now I think it is fine.
I think now it will be fine.
Yeah, sir. Can you please change one slide to make sure that everything is okay?
Now it will be fine.
Yes, now it's perfect.
Yes,
It
perfect.
works?
Perfect.
Yes, yes, perfect.
Yes.
Okay, that's good.
Yes.
Oof.
Oh, too much.
Well, the technique is very random. You never know when it's working really or not. Such a question.
And also, this is little different.
We know from a classical problem arising from the study of isolated singularity of minus Laplacian of u plus u2. So there is a really different aspect. Now, how to prove this? Okay, this is the first statement is very easy to prove. If P is bigger or equal to n minus 1 over n minus 2, then the constant LPn, which is here, okay, is is negative. Now you take a solution, you multiply by omega, and then, of course, on omega is okay. So there is no problem in this sense. In W1 to 0 of Sn minus 1 plus. And the first eigenfunction is cosine phi, and which is the arcsine of xn minus xn. Now you multiply just by cos phi and you integrate. And what you get this relation ln p plus 1 minus n times integral of omega cos phi ds plus integral of dsn minus 1 of omega ds prime is 0. Now, if p is between 1 and n over n minus 1, then this constant here, ln p plus 1 minus n is positive. Okay. This implies, of course, that omega on the boundary is 0, and then omega is 0 by opposite. Now, this is for the two cases of non-existence. Now for existence, we have to reduce a little the problem. First observation that any solution, so this is in the range, different range for the value of p. Okay, this is between n over n minus 1 and n minus 1 over n minus 2. First observation that the solution depends only on the angle phi, which is the angle with the vertical axis xn. How do we prove that? We take the average with respect to the variable in Sn minus 2. I call it, so it's a function which only depends on phi. I take this average and it defines this v bar of phi. Now the measure on Sn minus 1 is ds prime d phi. Second observation also, if I take this integral of the average of omega p minus 1 omega minus omega, the average of omega p to the p minus 1 times omega multiplied by omega minus average of omega, this is 0 because the first term does not depend on the integration factor. Now I make the average of the equation, I make the subtraction, and I multiply by omega minus average of omega, and I integrate. So what I have this term here, and plus this constant. And now for the boundary value, I have these terms. But these terms, I can write it like the average of omega minus, I can write these terms like omega p minus 1 omega minus average of omega to the p minus 1 average of omega because of this estimate here. And this term is bigger or equal when I've forgotten to multiply by omega minus omega bar, by omega minus omega bar here. And so this is bigger than 2 to the 1 minus p times omega minus omega bar to the p minus 1. Now we have to analyze the first term. So actually, omega bar is a projection of omega onto the first eigenspace on of the operator minus delta s prime, minus delta prime in W1 to 0 of Sn minus 1 plus. So the consequence is that the first term here is smaller than 1 minus n plus n minus. Okay, and I have these terms. So this is non-positive. And so the result is that in order this to be possible implies that omega must be equal to omega bar. So the function is equal to its average with respect to the variable on Sn minus 2. So it depends only on the first variable. Now, second, since it is a function only of one variable, it's a solution of an ODE. This ODE, I write it like this. So this is a new ODE. Now it's a rather standard analysis of this ODE, or this ODE, who says that a solution cannot change sign. Okay? So after this will be useful. Also now, other important fact, we have uniqueness also of positive solution. How do we do that? Okay, I suppose that I have two solutions, I make the difference. I have first equation, I divide by omega. A second equation with a new other solution, omega tilde, I divide by omega tilde, I make the difference, I multiply by omega minus omega tilde square. So what I get, it's very important that the first term is a negative contribution. And now the boundary term is this one. So this is boundary term, so this is negative except omega is equal to omega tilde. So this proves there is uniqueness. So now we know solution depends only on phi, they have constant sign, and there is uniqueness of positive solution. Now the question is about existence, but existence is not difficult because it's a one-dimensional problem. just I minimize among one-dimensional function. It should be here. The last term should be not omega, but eta. I minimize this functional over the space of radial solution, that means only depending on the angle phi, which belongs to H1 Sn minus 1 plus, intersected with L p plus 1 of the boundary, the relative boundary. Okay, and now with satisfying the boundary condition omega of sigma. This function only depends only on phi. And what I do, I write it like the sum of a function in H1 0 of Sn minus 1 and another function. So I can do this because I know that on the boundary function only depends on only on phi. So if phi is equal to 0, so it's a constant. So this functional is lower semi-continuous now in this space, and it's bounded from above by 0 and below by minus infinity, and it goes to infinity when eta in H1 Sn minus 1 plus intersected plus L p plus 1 Sn minus 1 dsn minus 1 plus goes to infinity. So it's after it's very standard to get existence. Okay, so we have existence by this very standard method. Important also to notice, remember that the first theorem says that there is no solution, no positive solution if P is bigger than n over n minus 1. But now what happened at n over n minus 1? Actually, it's a bifurcation point. It's a bifurcation point, but we have a branch of sign changing solution issuing from 0, omega is 0, and p equal n over n minus 1. So it's a bifurcation point. So we have the structure now of the set. These are the structure of the set. And what can we do? Well, when we know the structure of the set, we are going to try to analyze the singularity, the isolated singularities. This set E plays a fundamental role in the characterization of isolated singularities of this solution of this equation. I take it always, okay, it should be, sorry, this is minus Laplacian of u is 0 in omega, but it is not d minus du over the xn, it's du over d nu because it's in a domain, so I take the outward normal derivative. Okay. I look at this on the boundary. It's also very important that something which is a bit surprising from problem with strong absorption, that I have to make the assumption that u of x is bounded by c times x to the minus 1 over p minus 1. This is a key assumption, which is not at all natural for problem with absorption, but is very natural from problem arising from fractional operator. I will discuss this later on. Okay, this assumption I will do it. If I want to study singularities, I'm obliged to do this. Now, a second observation. If we have a solution of a problem in the half space, okay, if I have a solution of the domain in the half space, then I can make on the boundary an odd reflection, even reflection, sorry, even reflection. I define u tilde of x prime xn to be u of x prime xn if xn is positive, and u of x prime minus xn if xn is negative. So it's an even reflection. So this function u tilde satisfies this new equation, minus Laplacian of u tilde plus twice u tilde to the p minus 1 u tilde times the measure of the Lebesgue or of the n-dimensional, n-1 dimensional Hausdorff measure on dsn minus 1. So actually, with this even reflection, I transform a problem in the half space into a problem in the whole space, but the nonlinearity now has a coefficient which is a measure, and this measure is supported by the drn minus 1. So this is there is a strong assumption, but the assumption is not diffuse, it's localized. It's localized on the boundary. This is one reason for which, of course, the technique of Keller-Osserman doesn't work. But of course, it doesn't say that it is not possible. Now, the nonlinear problem with measure coefficients on the nonlinear terms, they have been studied by Jai and Verbitsky and colleague of Verbitsky, also by Saintier and myself. Saintier is a professor at University of Buenos Aires, and also, but in a slightly different framework, by Nathan Aguirre, who was presently my last PhD student. He's from University of Chile. Not University of Chile, sorry, University Católica de Chile in Santiago. So it's a way for handling nonlinear boundary problem, or to connect this type of nonlinear boundary problem connected with a problem with a measure potential acting on the nonlinear terms. Now, okay, I look now at the problem of isolated singularity. I look at this problem on isolated singularity. I consider a function u which is in C1 of omega bar minus 0. I suppose it is non-negative. It satisfies the equation minus Laplacian of u plus u is 0 in omega, and it vanishes. And on the boundary, it satisfies du over dn plus u to the p is 0, all on the boundary except the point 0. This is my nonlinear boundary problem with a possible singularity of 0. So what I have, if p is bigger than n minus 1 over n minus 2, then u is 0. We'll see why. Now, if p is between n over n minus 1 and n minus 1 over n minus 2, then we have an alternative. Remember, I assume that u of x is bounded by c times norm of x to the minus 1 over p minus 1, is equal. So in that case, now I have an alternative. In that case, when there exists singularity, either the solution satisfied limit of r to the 1 over p minus 1 u of r and sigma is omega of sigma. Remember, omega of sigma is a positive solution on the nonlinear bound, on the nonlinear problem on the sphere, on the half sphere. So it satisfies this. Either it satisfies this, or there exists some constant k, non-negative, such that, okay, if n bigger to 3, then x to the n minus 2u of x converges to k. And if n equal to, then u of x divided by minus logarithm of x equals to. So this is the first is called, I can call it a strong singularity. And the second case corresponds to weak singularities. Okay, so I have this characterization of solution with isolated singularity on the boundary for the equation with nonlinear terms with u to the p. Okay? How we prove that? The idea is to follow the old method which was developed by Mira and myself almost 30 years ago. The idea first, to flatten the boundary. You flatten the boundary using a diffeomorphism. And then this diffeomorphism, you change to x, you call it theta of x, call it y, and this y now you use spherical coordinates depending on y. Okay? And you write the new equation which is satisfied by u tilde of y. We call it u of x is u tilde of y, and now it's u tilde of r and sigma, and this is r to the minus 1 over p minus 1 v of t and sigma. So important fact that due to the estimate, the function v is going to be bounded. I take t is this is a standard M then transform, which to take T is logarithm of R. So since I'm looking to see what happens when R goes to 0, I look at what happens when T goes to minus infinity. Now for the variable sigma, it belongs to the half sphere. So what is the new equation satisfied by this? So it's a little technical, but essentially it has the following structure. In minus infinity times T0 cross Sn minus 1 plus, it is just a form of the Laplacian. It's a form of the Laplacian with this transformation. So it's what? It's 1 plus epsilon 1 times VTT plus n minus 2p over p minus 1 plus epsilon 2 times Vt plus ln p plus epsilon 3 times V plus delta prime of V. And then after that, I have a lot of perturbation, which are delta prime of this scalar product with some epsilon 4, then delta prime of Vt times epsilon 5, then delta prime of the scalar product of delta prime of V with En, which is normal vector in Rn minus 1, Rn plus, times epsilon 6. So it's a bit complicated. I'm going to explain a little what are those epsilon, okay? Now, how is transform the boundary condition? The boundary condition also will suffer from this transformation. So it's going to be Vt minus 1 over p minus 1 times epsilon 8 minus the scalar product of C and psi En, epsilon 7, plus delta prime of V times En times epsilon 7. So these are the perturbation. And now I have, which is important, the delta prime V times nu plus V to the P. So remember that, for example, if the boundary initially was a flat one, that means if the problem was in Rn plus, for example, all the epsilon G are 0. So it is just a perturbation of the problem in the flat, in a non-flat domain. Now, what I know, the function V is bounded by combination, about the derivative of these are bounded by combination of internal and boundary elliptic estimates. The positivity plays a very important role. And now the epsilon j are exponentially small because of the choice of the isomorphism theta. Okay. Now, important also to notice that any positive solution of my equation, minus Laplacian of u equals 0 or plus u is 0, which is, since it is positive, it belongs to L1 of omega, and it admits a boundary trace, which is a positive Radon measure. So this is essentially Ritz-Herlotz theorem. And I can write it, for example, like U is a Poisson kernel. U is a Poisson kernel, a Poisson operator acting on the boundary trace nu. Now the question in V, this one here, it admits a Lyapunov functional up, that means it has an energy structure up to epsilon perturbation. So you multiply essentially by Vt and you obtain something which is quite reasonable. On one side, and you integrate over Sn minus 1 plus times minus infinity times T1. And what you get the Lyapunov type structure here. This is a Lyapunov functional. And the other terms are epsilon, just epsilon perturbation. So they are integrable up to minus infinity. So it's not a problem. So after you have this, so when you have this, it means that since the function Vt, Vtt, and what prime of Vt is integrable up to infinity, up to minus infinity, then you can use after that the a priori estimate you have and prove that it goes, all those terms goes to 0. It goes to 0 and actually it goes to 0 in C2 of Sn minus 1. Now you look at the negative trajectory of the solution. Call it negative trajectory. And this is the union of all the points vt and dot is for sigma. And now you define the closure of this negative trajectory. And now you take the alpha limit set at minus, the limit set at minus infinity, so alpha limit set, and you define like this. So because of all the a priori estimate, the set is non-empty, it's compact and connected. So this is a property for all the limit set. Okay, also limit set of closed trajectory. Now we know that Vt, Vtt, and your prime Vt goes to 0 at minus infinity. So what is the result is that when you let t goes to minus infinity in the equation itself, and you say that Vt, Vtt, and your prime Vt goes to 0, so you are left with just equation satisfied the problem on the sphere. So what you know is that we know that the alpha limit set is a non-empty compact connected subset of the set of positive solutions. So we know that what is the structure of the set plus. Now, if we are in the case where the limit set is the set E plus is reduced to 0, so that means that the limit set is 0 and the solution V goes to 0 when tau goes to minus infinity. After, it's a question of linearization. You make some linearization and you obtain the result. Now, when the set is not reduced to 0, so it goes to the positive solution or to 0. So if it goes to the positive solution, since it is unique, you are done because of the fact that the limit set is connected. If it goes to 0, the limit set, you practice some linearization and you obtain that the solution decay like a solution of an equation without non-linear terms. That means with a potential, just a harmonic function. Okay, and some remarks that if P is bigger to n-1 over n-2, so the limit set here is also reduced to 0. And actually, in that case, we can prove directly that the coefficient k, the possible k is 0. I have not put it in the theorem, but there are no solution. In that case, the solution is necessarily 0. Okay? So I have the whole classification of positive solution of minus Laplacian of u in omega satisfying the u over dn plus up minus 1 plus u to the p is 0 on boundary minus 1. Now I would like to discuss a problem with measure. Problem with measure, if I make a formal integration of the equation minus Laplacian of u plus u equals 0 in omega with du over dn plus g of u is a measure equal to the measure mu on boundary, then I obtain this weak formulation. This weak formulation, provided the test function, okay, belongs to C1 of omega bar, Laplacian is in L infinity, and the normal derivative of the test function vanishes on the boundary. So this is a formal, if the solution was a regular one, this should be the expression. So this will be taken as a definition of a weak solution. If it's a formulation, if it's a weak solution, and we write it like this. So remember that important also that I take as definition of solution a function u in L1 of omega, but in such that it admits a boundary trace, which is a Borel function on d omega, because I want to define g of u on d omega. So I need this fact. Of course, all the construction will be like that. Now, I want to prove uniqueness for this type, assuming that G is increasing. Now, if you use in L1 with boundary trace in L1 of d omega, and if I assume that is a weak solution of this equation, then I have this expression. This is a catotype inequality. Then, well, A can be any real number. So I have this catotype inequality. This here. And this implies, I take now, if I take as minus Laplacian of psi plus, okay, in that case, A is 0, but with psi is this function is, say, for example, equal to 1, and then I obtain that the solution makes a difference between two solutions, and I obtain that the difference is equal to 0. So this is uniqueness as in all those problems with measured data. Okay. Now, question is about existence. Existence, there is an integral condition. This integral condition on the function g is the following. I assume that g is continuous, non-decreasing, vanish at 0. And for n bigger or equal to 3, I consider this expression, I call it the weak singularity condition at integral from 1 to infinity of g of s plus absolute value of g of minus s times s to the minus 2 n minus 3 over n minus 1 ds is less than infinity. Okay? I think it should be maybe 2n minus 3 over n minus 2, okay? But not very important. Now, this condition in the result that we have is the following, that if n is bigger to 3, and if my function satisfies this expression, 4.4, okay, then for any measure on d omega, there exists a unique weak solution to this equation. Okay, I tell you that it should be not 2n minus 3 over n minus 2 because the condition is not working actually here. It should be n minus 2 here, not n minus 3. The condition is not working for n equal 2. And now for n equal 2, we follow Vasquez's idea, which is to define the exponential order of growth of the function g. So a plus of g is the infimum of the a positive, such as integral of 0 to infinity of e to the minus as g of s is finite. Okay, and a minus of g is a supremum of the a which are non-positive, such that the integral of minus infinity to 0 of as g of s is bigger than minus infinity. So these are the two classical, I think this was introduced by Vasquez 40 years ago for analyzing the equation minus Laplacian of u plus g of u is equal to some measure in R2. Okay? And the result is the following. I assume that n equal 2. So if a plus of g is a minus of g is 0, then for any boundary measure mu, there exists a unique weak solution, uniqueness always coming from the monotonicity of it. Now, if a plus of g is between 0 and infinity, and a minus of g is between minus infinity of 0, and if I take special measure, mu is the sum of Dirac mass with coefficient a alpha j in R and boundary center in d omega, then there exists a weak solution to this equation, provided the alpha j is between pi over a minus of g, to be a minus of g here, not a plus of g, a minus of g, and a plus of g. So this is a similar result as the one of Vasquez, except that Vasquez also obtained his result for all type of measure. type of measure under the same type of condition, except that he write the decomposition, the Jordan decomposition of the decomposition of a measure like the sum of direct mass plus a measure with each which is diffuse with respect to direct mass. And actually, only important fact is that the direct mass is between pi over a minus of g and pi over a plus of g. So this is possible. It's possible that it can be extended to this equation, but there is a lot of work to do because it's not simple. Some notice here that if g of r is rp minus 1 times r for positive p, then a minus of g is a plus of g is 0. So that means that you can prove, you can solve the problem for any measurement. Now, if you look now, g of r is a sine of r times exponential of absolute value of r to the theta for a theta bigger than 1. So in that case, a minus of g is infinity, a plus of g, a plus of g is in plus infinity, minus of g is minus infinity. So you cannot solve the problem except with the zero measure. So these are two extreme cases. So now what are the techniques? The technique are, you use first your linear type estimate. You approximate the problem with smooth function, and then you solve the approximate problems by variational methods, not direct. Now you need regularity. The regularity for this type of problem, you know, two types of regularity. You need the regularity in the Lorentz space. That means also you can also call it that the Marcinkiewicz space. Okay, and you have this type of estimate for the linear approximation that uk in the space L n over n minus 2 infinity plus grad of uk in the space L over n minus 1 infinity is bounded by the L1 norm of the approximation and bounded by C2 times the norm of the measure. Okay, and now you have estimate inside, you need to have estimate on the boundary. For that, you need trace embedding and trace theorem in Lorentz Bezoff space, and these are the following type of problem. So you are obliged to introduce Bezoff space because you are working with Lorentz space. It's a bit complicated, but it's not so ugly. So you get this type of estimate. Now the trace of u on d omega in the Bezoff space d 1 over n, n over n minus 1 infinity, plus the second is more natural, uk in L n over n minus 2 of d omega, is bounded by what you have here. Okay, that means uk in L n over n minus 2 infinity and grad uk in L over n minus 1 infinity. So why is it important? Because the estimate we have in the Bezoff space allows to have weak convergence in L1 and L1 of d omega, and also almost everywhere convergence. Okay, they are relative, of course, so for the respective Hausdorff measure on L1 and of omega and L1 of d omega. Now the question is also always to obtain the you have the convergence of the G of UK almost everywhere, but the problem is to have a convergence in L1 of the boundary. And here again, the trick is Vitali convergence theorem, and this is just an adaptation of the classical technique, which was been introduced actually by Bresis and Demina a very long time ago for a similar problem inside omega. And okay, this I like this. You say that you look at the set of x in d omega such that absolute value of uk of x bigger than lambda, and then you have the measure of this set, that means the measure of the boundary. Okay, is I call it alpha k of lambda, and it is bounded by c times the measure of d omega times lambda to the minus n minus 1 1 1. Why? This is just estimate in the base of space. This is a boundary estimate. Okay? Now you want to prove how to use the Vitali theorem. Okay, you take a small set, a boundary set, a Borel set, and then you write like this: integral of g of uk is bounded by g of lambda minus g of minus lambda times the measure of E minus the integral of g of s minus g of minus s for the measure d of alpha. And then what you get, your integration by part, and you obtain this one, you obtain this expression, and now you make this, you fix lambda so that this is small enough, epsilon over 2, and now you fix E so that this is smaller than epsilon over 2. So this is, you have a uniform convergent, and then you have okay. Now when g of r is rp minus 1 times r, the condition is satisfied provided p is less than n minus 1 over p minus. Notice also that when you make k goes to, you look at, so assume that you are in that case, and you let k goes to infinity. You assume that you look at a solution uk delta 0. So you look at this solution and you let k goes to, you know that k times uk of delta 0 is increasing. And now you let k goes to infinity. So what happens? If there exists a, if u is bounded by constant time x to the minus 1 over p minus 1, then we know that the solution uk delta will converge to a solution with a strong singularity at 0. It satisfies this. Now, but this, of course, it's important to have that existence of this solution of omega s. So if omega s does not exist, so the solution uk delta goes to infinity. So this is a very strong difference of that proves that in the case at least when p is between 1 and n over n minus 1, there cannot exist a universal a priori estimate of Kähler-Wassermann. Okay. This is something, this strong diffusion phenomenon is very typical of equation with a superlinear absorption and fractional diffusion. So this was pointed out in a paper that I've done with Hui and Chen, and concerning this equation, minus Laplacian to the 2s u plus u to the p in omega minus 0, and when s is less than 1 over 2. So it should be, this is for small value of s that this happened. And also, this is something that we pointed out with Yan Chen and Ying Wang for concerning this equation. So there is a very strong difference between the case where this is a pure Laplacian type and the fractional Laplacian type of or a non-local operator. You cannot have an Wassermann type estimate. I have explained that the method doesn't work, but actually it cannot be if S is too small. Okay, now the question, there is an open question, is if there exists a universal estimate that times not a non-universal estimate. I'm sorry. Does it exist a non-universal estimate for a positive solution of the nonlinear problem of the type u of x bounded by a constant depending on u times x to the minus 1 over 2? So this I don't know. This is really open. Okay, now I'm going to say a word on. Okay, a word on in the case where the measure is not admissible, that means you can take any measure. So in that case, the question is usually you have to take a measure which is not too much concentrated. For example, if p is bigger to n minus 1 of n minus 2, you know that you cannot solve the problem with a Dirac mass because it is too concentrated. So you have to take a measure which is a little more diffuse, and diffuse is respect to a capacity. And so you assume that p is bigger to n minus 1 of n minus 2, then you can solve the problem 414 for a measure, a positive measure, well, you have always uniqueness, if and only if the mu is absolutely continuous with respect to the C1p prime capacity in dimension n-1. So it is a Sobolev or Bessel capacity. Since it is C1p prime, it is the same. Okay? And as usually, the main observation is to look at the linear problem, and to see under what conditions the solution of the linear problem is such that you take the p power of the solution, and you want to see if it is integrable on d omega, the trace of d omega. So this is, and this gives naturally the singularity. It gives you naturally the capacity. So this is okay. So I will not go too far. How much time you have? I don't hear you. You just say like this.
Okay, so 5 minutes maybe.
How much? 5 minutes?
Yeah.
Okay, that's good. So, okay, I'm going to develop just a little in that case. So you look at this problem, and now this problem, it's a Neumann problem, okay? And it admits a solution. I call it V is n of mu. And the fact that V is an LP of d omega is equivalent to say that mu is in W minus 1 P prime, P of d omega, with equivalence of 1. And this is proved by duality and regularity and of the Dirichlet to Neumann operator. Okay? Now, if you take a measure mu, okay, it's important is that if you have a measure in if you have a measure such that the n of mu is in W is integrable on that the function v is in LP of d omega, this function v is a natural super solution of the equation. So if you have a super solution of the equation, of course you can hope to have a solution below, and this solution, this super solution is such that the v, this is this expression, the power of v and the trace of v of d omega to the power p belongs to LP. So it's good. That means you are in the good configuration. So now you take a measure mu in W1 minus P. It should be minus 1P, I'm sorry. With the positive, it's in, you take measure, mu in W minus 1P of d omega. And then the Neumann operator of mu is a super solution, and it satisfies, it has a good integrability condition. And you solve the problem. Now you can solve the problem with truncation. Now you can solve the problem with truncation, and now you let k goes to infinity, and then it converges to some solution which satisfies the equation. So you have a solution. So this is when mu is belong to this space, it's good. Now, if you have a positive solution also, if you take a compact subset of d omega, you take a function eta, which is C1 with compact support on d omega, with value between 0 and 1, and eta equal 1 on the set E. I'm sorry, I've forgotten to write on the set E here. Then you integrate, and what you get? You get the integral of d omega of up to the eta prime, yes, plus C times integral of d omega of up to the eta prime to the 1 over p times the norm of eta in W1 p prime of d omega. So this is bigger than the mu of E, because remember that eta is bigger or equal to 1. So this proves that if the measure, now if eta goes now to 0 in W1 p prime, so this goes to 0. And it proves that the mu is absolutely continuous with respect to C1 p prime capacity. So this is observation. So you have possibility of having a solution. Then you know that if you have a solution, then the measure must be absolutely continuous. And now how to characterize all the absolutely continuous measure. So this is a result, classical result, which is due to Fayel and de la Pradelle and also Ambrosio. If you have a measure, which is a positive measure, which is absolutely continuous with respect to this C1 P prime capacity, then there exists an increasing sequence, mu k, which belongs to W minus 1 P of d omega intersect with M plus of d omega, which converge to the measure mu. Okay, now for such measure mu k, you have a solution uk. Now you have a solution uk because it belongs to W minus 1 P of d omega and solution with mu k. Now you can go, let k goes to infinity. So uk converge to some solution u, and you solve the equation. So now a consequence of this is that if k is a compact subset of omega with positive capacity, C1 P prime capacity, there exists a positive function u satisfying minus Laplacian of u plus u is 0 in omega, du over dn plus up is 0 on d omega minus k. That proves that a set which has a positive C1 P prime capacity on boundary is not removable. And of course, the main problem is to know under what condition is it a necessary condition also. And the question is, it's a real conjecture to know that if you have a set k on d omega with capacity C1 P prime of k is 0, does it imply that k is removable? That means you have identity. This is not. And for most of the problems involving a fractional operator or non-local operator, I have the same difficulty. Okay. So thank you for your attention.
Thank you very much, Professor Lauren Veron, for such a wonderful talk. Now I request the participants to write your question in Q&A box. If you have any questions or comments, anything, please write it in Q&A box. We'll take it up. We have received few of the questions in Q&A box. Shall I convey it, the questions that we received here in the Q&A box? Okay. So the first question is, I think I can see is written to show existence in first theorem, you use minimization technique. Is there any other technique?
Well, I think it's not, because you know it's a perturbation of a convex functional. So it's natural. It's a quadratic perturbation of a convex functional, which is bounded from below. So it's natural, I think, to look at minimization. Okay, which is an important fact is to notice that before looking for existence by minimization, we have been obliged to reduce to show that the equation depends only on one parameter, on the angle phi, on one variable. Otherwise, I could have not done the reduction. That means the solution is if it is a one function, it's a function depending only on one variable. So the boundary value is a number. So after that, it's very simple to take that. If I take the function minus its boundary value, it belongs to H1, 0. And this, otherwise, if it were not the case, I don't know how to prove it. Maybe by other techniques like mountain pass, it could be possible, but I've not tried because I've already one proof, and it covers all the cases.
The second question I see here, it is in equation 2.1, is LNP related to the eigenvalue of Laplace-Beltrami operator or the curvature of any?
No. The LNP comes directly from the, look at the solution. U of x is U of r and sigma is r to the -1 over p minus 1. So if you assume that u is an harmonic function, then you will find immediately, if you have an harmonic function which is under this form, you will see that it satisfies this equation here with this LNP. This is just the fact that it is an harmonic function, and you assume that this harmonic function has this expression here. This expression here, you look like this. So you are obliged to have this function. After that, of course, which is very important for existence, is the value of LNP with respect to eigenvalue of the Laplace-Beltrami operator. But in that case, and this classification of comparison of LNP with respect to eigenvalue of the Laplace-Beltrami operator depends on P, exactly on P. Okay? So this is always, you can take an harmonic function, you write it like this, and you will see that it satisfies. Okay?
I think the next question I can see written is there any explicit character? No, it's not. What about the general G instead of non-decreasing? What could be possible difficulty one might face of general G?
Okay. For general G, there are many, okay, people have worked on this type of equation with G of U is my function G of U, or U to the P, is minus with a negative terms. And so this is a different point. It's a really different point of view of it's a very different analysis. It's a completely different analysis. And for example, if G of U is minus U to the n of n minus 2, so this equation plays a very important role in geometry. This equation of deformation of a matrix in order to fix the Gaussian curvature on the boundary. So this has been studied a lot by, for example, by Escobar and by Cherrier. So the other nonlinearity has been studied with other side nonlinearities, that means it's not absorption, but when it is a source, it has been studied by people working in geometry. Now, if you want the nonlinear problem with measure, in some sense, okay, the monotonicity can be a little weakened. It can be weakened, but you have to have a function which is positive at plus infinity, which is negative at minus infinity, and you have this function should be bounded by a function which satisfies the weak singularity assumption, by a non-decreasing function satisfying the weak singularity assumption. So the fact that the nonlinearity is monotone can be a little modified, but you need a absorption nonlinearity. This is for this type of problem. This is really the real core of this problem, is to have a absorption nonlinearity. Okay.
So I see a question from Huyan Chen. So he has written, can restriction 3.2 be weakened for the non-existence in theorem 2? Here the operator are all local.
This P bigger than n minus 1 of n minus 2. And in the theorem, you say in what is the theorem?
Theorem 2. Yes, theorem 2. Can restriction 3.2 be weakened for the non-existence in this theorem?
Well, in that case, it proves that the singularity is removable. Essentially, if P is bigger than n minus 1 and n minus 2, then the singularity is removable. So there is no singularity at all. So that means that the equation is satisfied. It's satisfying minus delta U is 0 in omega, and du over dn plus u to the p is 0 on d omega. So you after that you have no singularity, so it's a monotone problem, and you have 0. The only solution is 0. But it is you see it's between you compare 1 to 2, so you see that it is sharp. You have there is no possibility of playing with that. The question, the main question, for this problem, I think the main question, okay, non-negative solution is important because of the technique we use. It's not easy. It's not really a problem like the minus Laplacian of u plus u to the p is 0. Maybe it's come from the fact that it has a fractional structure, fractional Laplacian structure, and for me the main problem would be try to understand a little the a priori estimate. What kind of a priori estimate could it?
I see another question. It says that is there any development if one include potential terms, say Hardy potential? So maybe with Hardy potential and the boundary, normalized boundary trace in terms of that something.
You can develop clearly. You can develop this type of things. This is you have to mix different machineries, but clearly you can develop it. Will shift many phenomenon, and maybe new phenomenon can appear. Could be of course of interest to try to understand this, to replace even the operator itself by a Schrödinger, but not as a Laplacian by Schrödinger operators. No, I think it could be interesting to develop this type of analysis.
I see one more question. Johannes Osborne, he has written, thank you for your talk. Could we search for solutions that are not separable?
Well, I think the question is, if you have solutions which are not separable, it's very difficult to have a precise behavior on the boundary. It's very difficult to have precise behavior of the boundary. You may say that either the solution is harmonic type, or not of harmonic type, but you cannot hope to have a precise expansion. Because the non-linearity has exactly to be known, because you can say, well, for example, we can replace u to the p by some function g of u, which behaves like u to the p when u goes to infinity. So I believe that in that case, for positive solution, you can have by scaling technique, you can have the same type of characterization of solution converging to a solution of strong type. But only for positive solution, because you cannot use a technique of energy, except also that if the non-linearity satisfy, Musumi, this type of papers that you have done with Moshe, that you have a non-linearity which has some invariance with respect to scaling. I think that for this type of problem, maybe you can say a little more about the problem. I think it's a technique that you have developed with Moshe at this time, maybe could be applied to understand the a priori, the expansion. I let you.
So I think one more question I see from Rinmai. He has written, is there any explicit characterization or asymptotic estimate for solution for particular measures, a Dirac measure? Is there any explicit or asymptotic estimate for solution?
Well, for direct measure, you know exactly how does it behave. You can also have solutions which are maybe, say, for example, one-dimensional, a uniform Dirac measure, which is a uniform Dirac measure on a k-dimensional submanifold of the boundary. So it's possible probably to obtain an expansion, but I think it's much work. It has to be, I think if it's much work, and if there is a good reason, maybe If not, I don't know.
Okay, so one more question from Anup Biswas. He's written, if we have two singular points at the boundary and the blow up at the singular points are of different order, then what can we say about existence and non-existence?
Okay, no problem. It's since the problem with absorption, you can have many types of boundary blow-up. You know, you can have different type of blow-up with one blow-up with a one blow-up with a say Dirac mass blow-up and another blow-up with a strong singularity blow-up. There is no contradiction, no problem at all, because in some sense, because it is on the boundary there is some coercivity, you know, not inside, but on the boundary there. So there is no influence of one point to another point. You can, okay, for example, you can solve the problem with measure, a sum of direct measure on the boundary, and you let one coefficient goes to infinity. So there is no problem for that.
I have just a very naive question. So since here the problem is for the absorption term, so for the source case, the problem is well defined, or I mean not this analysis. I'm saying that one can study the problem for the source case.
Okay, the problem with source case, you have two types. You have two types. There are people working in geometry who have studied this problem with G of u is minus u to the n over n minus. This is a lot of people working in geometry. Now with problem with, I think with problem with G of u is minus u to the p, probably up to p equal to, I think, could be maybe the same value. It could be n minus 1 or n minus 2. Then you can solve this type of equation. There is, I think the technique has to be modified, very strongly modified. For example, you have to look at the problem. Look at the two types of equation. Minus Laplacian plus uq is measure mu, or minus Laplacian is equal to up plus mu. You see, you look at the problem and try to analyze exactly what is a different approach of this type of problem. There are many things, there are things in common, a lot of things in common, but for example, when you have a problem with source, you know that you can solve the problem provided first that the measure is not too concentrated, and second, that the mass of the measure is not too large.
Yes.
Here, it's a question only on concentration of measure. So you have, the people have to understand, to read carefully the paper of I think Adams and people by Adams and Pierre, also with PDE, Jai, Verbitsky, and so on. Many people have studied the problem with the source term, even with Mazia, Verbitsky, and so on, 30 years ago. And the problem with the measure inside, holding the boundary, which has been studied first by Barras and Pierre and then by Moshe and myself as well. So you see, after analyzing those two types of problems, probably there will be a way to study the problem replacing a absorption by a source. And I'm almost sure that the question will be, or the answer will be at the same time.
Okay. Thank you very much, Professor Veron, for making this session successful. And we hope to get your participation in future talks as well. Yeah. So thank you very much once again.
Pleasure for me.
Okay, so for participants, I have the announcement. We will meet on next Tuesday for the talk of Professor Stefano Bianchi on Euler equations. Now, I request all the participants to leave the platform. Thank you very much. Thank you, Professor Veron.
Thank you very much. Pleasure for me.
Thank you. Bye.